So in this video, I'm going to go ahead and talk a little bit about Le Chatelier's principle and how it relates to the experiment we're going to do in experiment 4. So this should help you with your pre-lab assignment. So first, let's consider a reaction. So let's consider that we react A and B. So these are our reactants. And we start with just those in the flask, so there's high concentrations of those, and those react, collide, and form C and D. So what happens is that we can form enough C and D in our flask, and if it's a reversible reaction, which let's consider this one is, C and D can react to produce A and B. So we have the forward reaction, which is A plus B forming C and D, and then C and D can react to form A and B, which is the reverse reaction. So we can write this like so. It's a reversible reaction, and so this reversible reaction will show A and B forming C and D with those arrows showing the forward and reverse. And essentially, if we're at equilibrium, as we talked about in class, the equilibrium means that rate of the forward reaction equals the rate of the reverse reaction. So basically, this reaction at equilibrium can be disturbed, can be stressed. Okay, so ways that this reaction can be disturbed is that the temperature can be changed, or the concentrations of the reactants or the products can be changed, or if it's a gaseous reaction, changing the pressure will cause a stress on the reaction. So in the lab today that we're going to talk about, we're going to consider temperature changes and concentration changes, and this is also what we will consider in experiment 4. So Le Chatelier's principle simply states that if a reaction that is at equilibrium is stressed by those ways we talked about, that reaction is going to shift in order to relieve that stress. So it wants to get back to that equilibrium state. So if we disturb that reaction by stressing it, that reaction will shift to relieve the disturbance or the stress. And it gets back to its equilibrium state. So we're going to look at a few examples of this in the next couple slides. So we're going to go ahead and look at an example equilibrium system and how we would set up this system in lab and how we would shift it according to Le Chatelier's principle. So this reaction is copper 2 plus 4 moles of bromide forming a complex ion, copper with 4 bromides at 2 minus charge, and this reaction is exothermic, so I'm going to have plus heat. So the copper 2 plus is blue, and the complex ion is yellow. And this is going to allow us to see how our system is shifted using Le Chatelier's principle. So first we need to set up this system. So the reagents available for us in lab to set up the system are copper 2 nitrate, potassium bromide, and silver nitrate. Okay, and these are the reagents we're going to use to set up the system and to shift that equilibrium using Le Chatelier's principle. So what will we put in our test tube, what reagents, to set up this equilibrium system? That's what we first need to figure out, and that's what you'll be doing in experiment 4. So we look at our equilibrium reaction, or our reversible reaction, and if it's at equilibrium, we have our copper 2, and that is found in our copper 2 nitrate. So we want to add our copper 2 nitrate to our test tube to get our copper 2 ion. Also, looking at our reaction, we need bromide. Where can we find bromide? Potassium bromide. That'll give us potassium bromide ions, or potassium ions and bromide ions. So that provides the bromide. So essentially in our test tube, we put in the copper 2 plus and the bromide, and that's going to go forward to make our yellow copper with the 4 bromide 2 minus. And in this case, if we put in the test tube, we see blue. Okay, so actually the copper 2 plus is favored. So if we want to shift this reaction to the right, to the yellow substance, what will we add? Well, we can increase the concentration of our copper 2 plus ion. And if we increase that, add that, it's going to shift the reaction to the right to relieve the stress, to get rid of that added copper 2 plus. or we could add more bromide ion. Okay, so we could add our copper 2 nitrate to give us more copper, or potassium bromide to give us more bromide. In each case, the reaction wants to shift to the right to get rid of that added copper or bromide, so to turn yellow. That's what we would observe if it shifts to the right, to the yellow product side. So the reaction to show this shift is quite simple. There's no new chemistry going on. We just are adding the concentration of one of the reactants. So we can just write the same reaction, our copper 2 plus our 4 bromide ions. But now we're going to the right, so I'm showing a right arrow forming the copper with the 4 bromide ions 2 minus charge. I'm going to ignore the heat, right? So it's going to the right, so I'm showing that right arrow. All right, so now let's say we want to shift the reaction to the left. So we want to get back to our blue solution. What could we add? Well, the only substance that we have available that we haven't added is our silver nitrate. So if we add that, it's actually going to shift the reaction to the left. And you might be thinking, why is that? What is going on here? Well, silver nitrate gives us silver ions, and silver ions will react with the bromide ions to form silver bromide precipitate. If you remember your solubility rules, you remember that silver bromide is insoluble. So essentially what's happening here is bromide is removed from our system. So the reaction wants to shift to the left to replace that that removed bromide, right? It wants to relieve the stress. So the reaction is going to shift to the left to replace that bromide that was removed by the reaction with silver. So if we want to write the reaction to show this shift, it's going to be a little more complicated than last time because we actually have some new chemistry going on. So I'm going to start with our equilibrium or a reversible reaction, our copper 2 and our 4 bromides forming our yellow complex ion. So that's what we're starting with. And then we added silver. So I have to add silver to both sides of the reaction. And I'm going to add 4 moles of silver to both sides because I have 4 bromides. So it's a 1-to-1 ratio of silver plus 1 to bromide minus 1. So that actually forms our silver bromide. So we're shifting, so I'm going to add these reactions together basically. We have our copper 2 plus and our 4 moles of silver bromide solid. And I'm going to show a left arrow because that's the direction we're going. And we have our complex ion plus our 4 silvers, right? So it's shifting to the left. So our reaction in our test tube should turn blue because we shifted towards the copper 2 plus. But also we formed in a side reaction some silver bromide precipitate. So we should see some precipitate at the bottom of that test tube. We're still going to look at the same equilibrium system. I mentioned it was exothermic, that heat was a product, so I've kind of ignored that so far. So heat is released, exothermic reaction. I mentioned at the beginning that changing the temperature is a stress that causes the reaction to shift, so we're going to investigate that here. So if we have our test tube, we set up our equilibrium system as we discussed earlier, and if we have our our blue solution here, we want to shift this reaction to the right to make it yellow, and we want to change the temperature. So what we can do is we can put this test tube on ice. And what happens if we put this test tube on ice? Well, we're removing heat. And if we remove heat, the reaction wants to shift to the right to replace that removed heat. That's what Le Chatelier's principle says, that the reaction shifts to relieve the stress imposed on the system. So putting it on ice removes heat. The reaction will shift to the right to replace that heat since it's an exothermic reaction and heat is a product. So we should see that the solution, the blue solution in the test tube, turns yellow when we put that test tube on ice. So now if I want to shift back to the blue solution, so I want to shift the reaction to the left, what can we do? We can heat the test tube in a hot water bath. So that is adding heat to the system. And if we add heat to the system wants to shift to the left to remove that heat, and it shifts towards the reactants, which is our blue solution. So our yellow solution, when we put it in the heat, should turn back to blue. So it's shifting to the left, turning back blue. Okay, so we're going to look at one more example, and this is actually something you have seen in the past in Chem 1A, which is our phenolphthalein indicator. We use this in our titration lab because phenolphthalein is an acid-base indicator. And so phenolphthalein can be protonated, and I'm going to write this as HIND, so IND represents the indicator molecule. And so they're attached, and in the forward direction, that can break apart into H+, separate from the indicator molecule, which is IND-. And so when it is protonated, when it's in the HIND form, that is a colorless molecule. And when the proton is removed, that is a pink. The solution is pink when it's in the IND- form. So if you remember in our titration, we had a flask. In our flask, we put our acid and the phenolphthalein, that indicator. And we remember, hopefully, that it was colorless at this point because it's in the HIND form, the colorless form. The acid protonates that indicator, and it is colorless. If we have our burette with base in it and we add base to this flask, what happened? Well, it turned pink, right? And so that means that the IND- is being formed. And why is that? What's going on here? Well, we're adding base. We're adding OH-. So I'm going to add OH- to both sides of this reaction. And the H+ and the OH- react to form water. The H+ is being removed from the system. And we have our IND-, the pink. And we have the HIND plus the OH-. So I'm showing the reaction here. So our reaction is shifting to the right. We're removing the H+ ion by adding hydroxide, forming our pink IND- substance. So hydroxide changes the concentration of H+ because it reacts with H+ to form water. So we're removing the H+ from the system. So the reaction has to shift right, the forward direction, to form more of that H+, to relieve that stress. Right? That's what Le Chatelier's principle says. So that's why we see the pink. So how are we going to shift the reaction to the left, to the colorless? Well, we can add acid. We can add H+. We can increase the concentration of H+, so that reversible reaction seen up top, right, will shift to the left, forming the HIND form, which is the colorless substance. And so I'm showing that here. That was no new chemistry, so it's simple. The H+ is just reacting with the IND- to go to the left and form the HIND colorless solution.